All right. So today we're going to talk about some issues involving glass transitions, and some of this is mostly a review, so you guys really understand these concepts, but you might see them packaged differently on this on the final, which is where we're starting here with this material, or actually Friday's material. A lot of this should seem familiar, but I wanted to go over it again just to make sure you have a sense of where we are with actual real polymers. And so the issue here is that these are pure polymer TGs, but of course we experience plastics in their impure forms. But in looking at these, we should be able to rationalize the structures that we see and the resulting glass transitions based on what we know exists inside these polymer structures. And so, as you should be aware, it's a balance of nonpolar and polar bonding, and the polar bonded materials tend to have higher melting points, higher glass transitions, and the nonpolar systems tend to have lower melting points and glass transitions. And all these things should seem reasonable. And there's a bunch of polymers here that you've never heard of before, and this, again, as I keep saying, this is a small fraction of what's out there. But things that we are familiar with: polyacrylic acid, PMMA, polystyrene, polyacrylonitrile, PVC, polyvinyl alcohol, PET, of course, and let's see. Well, I'm familiar with a lot of these, but some of these you're not familiar with. Polymethacrylate. Let's see. Polychloroprene, we talked about that. Let's talk about it again today. Polypropylene oxide, polyisobutylene, natural rubber, polyisoprene, PDMS. All right, so all these things have very different glass transitions. And so just to pick on one, if we go to polystyrene, it's easy to remember. It's got a TG of 100 degrees. All right, which suggests that polystyrene should be useless to us in pure form, and certainly it is. But as you now know, we toughen the heck out of it with rubber, for one thing, in a variety of different ways. And also we make sure that it's amorphous so that it doesn't have all the crystallinity that makes it even more brittle than just the glassy form would otherwise dictate. And remember, the TG is part of the amorphous state and TM is part of the crystalline state. All right, so we want to make sure it's purely amorphous, because you add crystals to it, it becomes even more brittle. But of course what we do then is toughen it with rubber and make some of these issues less of a concern. But so as you've certainly learned by now, with plastics, it's a balancing act between a lot of different things. And hark back to ABS, which is a great example of pulling things together into one polymer structure and getting it to do what you want it to do. That is, pieces of this all in one polymer. All right. So hopefully we're getting a feel for that at this point in terms of how we design plastics to achieve certain properties and do certain jobs for us. And so but the high temperature glass transitions, and of course we see these as being relatively brittle materials, also meaning that they have good mechanical properties if we need them. And again, polystyrene is deliberately toughened. Polyvinyl alcohol has a ton of plasticizer in it, so some concerns about what that plasticizer does to us in the drinking water, but compared to lead, it's probably a lot better than that. But as you should know then, but these are never pure. But in this state, we should be able to look at this and try to rationalize some of the behaviors that we're seeing as far as glass transition. And of course, melting point is going to mimic glass transition. The other end of the spectrum, we have the softer materials. All right, the rubbers and PDMS. All right, and PDMS is down here at the bottom of the chart. Why? And you remember why PDMS is way down here? What does PDMS do? The chain itself, the SiO-Si chain. Yeah.
Isn't it like you can rotate around those?
You can rotate around those bare oxygens in the chain, right? And you also have this huge range of bond angles, not just 5 degrees like you do for the carbon sp3 bonding. We have 70 degrees of allowable bond angles, I believe, for PDMS. So it's got this huge range that makes it natural for this spot in the chart. All right. So via architecture bonding, we control these properties and then control the areas in which they can be used. All right, so other factors that affect glass transition, and this kind of gets into some of the details of glass transition that we haven't really talked about before. One of the things that should make some sense to us at this point in the class, polymolecular weight. And there is a slight relationship. I say slight because it's very important over a certain range, and then beyond that, not so much. And we've seen this in other things as well, that polymers, plastics tend to be high molecular weight materials, and some of the factors that are important, that especially involve chain ends, are really important when the chains are short, and then when the chains are really long, those chain ends become so rare that, if there's a dependence, it's hard to see. Now, this is another example, but there is a general relationship between TG and molecular weight. Increases in molecular weight increase TG. Oh, I don't have my pen here. Anyway, but when molecular weight is very high, further increases only slightly increase the glass transition. And so we do have this relationship for TG as being equal to TG at some infinity when this molecular weight is very, very high or infinite. And then we have the alpha sub r and alpha sub g, the thermal expansion coefficients for the rubbery and the glassy states respectively. And so there is this relationship. It's not that important, but in general, we tend to think of as the molecular weight goes up, the glass transition goes up. But looking at this chart, you can see why I don't regard it as being all that terribly important, because when n, we talk about the number of repeat units n. In this context, we're talking about the same thing. Relatively short, this could be polystyrene. Actually, it might actually be polystyrene since the way it tops out. But we get above, around 1,000 or so of these repeat units. And after that, it's pretty much a constant. All right, and so we should understand why in terms of the effects of free ends, and we'll hit on this again today. Free ends have an outsized influence on mobility in their local area, but if those free ends become really, really rare, it's not going to really have a big effect. And that's what's happening when n goes beyond 1,000 for this particular polymer, which again I believe is polystyrene. And so you should be, as it says here, be able to explain this from the relationship between molecular weight and chain interactions. And so, lots of polymer aspects in polymers have to do with how rare things are in polymers. And then when they start being rare, they may stop being particularly important. All right, and so this is all driven by the fact that every chain end has some free volume associated with it, which we've discussed at length. The low molecular weight polymers contain shorter chains, has more chain ends per unit volume, so there would be more free volume. All right, and so the best way to think about this is when we have this chain end, it has this envelope, this cloud of free volume around it that not only affects its own chain, but can affect neighboring chains as well. All right, so everything that surrounds this area here is going to experience easier motility, more mobility, can vibrate in response to temperature more readily. All right, but if this is just one small area in the middle of an infinity of longer chains, it's not going to have a big effect. All right, and so just to take it to extremes, if you have, for example, crystallinity in the system, you may cause a little bit of early melting here in this area where the chain end is, but if there's only a few of these, you're not going to be able to see this in the DSC. All right, the rest of it's going to be far away from that, so it's all going to melt where it's supposed to melt. This area might have early melting, but there's so few of it, so little of it, it doesn't affect macroscopic properties or even the DSC analysis, if that makes sense. And so higher free volume, of course, means more motion. We need lower temperatures to freeze it, hence the glass transition for shorter chains will be lower than TG for longer chains. And so again, when we think of glass transition, it has to do with how much energy or how much temperature is required to cause those chains to move apart and go to this realm of a higher thermal expansion coefficient, associated with the glass transition. And so whatever makes that more difficult will raise the glass transition, and whatever makes it easier will lower that glass transition. All right, chain flexibility is also a significant issue. A polymer with a backbone that exhibits higher flexibility will have lower glass transition. And this makes sense because the activation energy for chain motion is also going to be lower. All right, so going from this below TG state to the above TG state is driven by how easily that chain can be moved. And so if we have a repeat unit as shown here for polyethylene, glass transition is 133. In contrast, we have this, I believe this is phenylene oxide, and what makes sense here for the polyethylene is that we just have CH2, CH2, no polar bonding, all right? Chains move easily. It's just hydrogens on these carbons, and those are pretty small, all right? So it makes sense it doesn't take much energy to cause that to move. When we look at phenylene oxide, on the other hand, we have a couple of competing influences. One, we have that free oxygen, which we remember is part of why PDMS is so flexible. So this has no side groups around it, so it should allow things to spin. That's why PET is PET, because of that very fact. But when we take that and couple it with this phenyl group, big, heavy, bulky, all right. Again, remember that we draw these things. This 6-membered ring is, and this sketch is about the same size as the oxygen atom. We know that's crap. All right, this is 6 carbons, so it's this huge trundly thing with a little oxygen next to it. All right, so again, be careful when you look at these shorthands that we have for structure. And it turns out that actually dominates the glass transition, because even though the oxygen should drive it down, that big, large group drives it back up again, all right, in terms of glass transition. So hopefully that all makes sense. And so the one polymer that you now are going to have to memorize, the new one at least, is polycarbonate. And so we can look at this in the same context. And so here we have a couple of these phenyl groups. All right, again, much larger than what's shown here in real space. We also have some polar groups as well, all right, that can hydrogen bond with neighboring hydrogens in the structure, wherever they're coming from. All right, and so that's certainly significant. But of course, we also have the fact that these are going to allow that chain to spin. And so polycarbonate, I don't want to leave out the fact that we have these CH3s here. And they're CH3s, they're not very large, but they're certainly larger than hydrogens. All right, so these guys are going to cause some interference as well. So it's obviously a mismatch of things that drives this glass transition up to 150 degrees Celsius, all right, which says that polycarbonate should be a relatively rigid plastic. All right, we wear it on our faces, and it's useful there because we want something that's rigid. I can tell you it's not pure polycarbonate. All right, there's stuff in there for a lot of different reasons, but it still is a relatively rigid, what we call an engineering polymer. Yes.
If on a test, like on that first problem, it's polycarbonate, what's the abbreviation for that?
PC?
PC?
Yeah. Yeah, there's no recycling number with it. It doesn't get recycled enough to have a number. Any other questions? All right, and so side groups are also a factor here in that they give rise to this phenomenon called steric hindrance, which you're familiar with. Larger side groups hinder chain motion more than smaller ones. Therefore, polymers with larger side groups tend to have higher glass transitions. And so again, we look at this set of polymer structures, the standpoint of a simple algebraic notation. If X is CH3, polypropylene is minus 23. We add a longer chain onto it, it gets more difficult to move around. Then TG goes up to 50, and then we produce polystyrene, and we get to 100. Right? And so also do how easily things can move and what they can do to influence the glass transition. And so we know that for polystyrene, we have the glass transition of 100, and then we have this, we add instead of the hydrogen here, we add a CH3, and so things get larger and more difficult to move around pretty substantially just by the addition of a CH3 for that hydrogen. So you could tell the system is very sensitive to the issues of steric hindrance. By adding a CH3, we boost the glass transition by 75 degrees centigrade. And then we have these polyphenol groups, which can drive things up, but surprisingly not as much as the addition of the CH3. All right, so we can engineer these structures, engineer the mechanical properties, and basically engineer what we can do with the plastics based on these changes in architecture, as it's called. And then, again, something you've seen before, polarity, increased intermolecular interactions, decreasing chain mobility, thus driving TG up. And so you guys have seen this previously, CH3 versus these other groups that can actually mount some type of polar bonding between neighboring hydrogens in these chains and drive the glass transition up substantially. All right, so getting a little bit further out, branching is significant as well. Polymers with branches have more chain ends and so have more free volume. All right, and so these types of structures and their influence kind of depends on how long these branches are. All right, so it gets to this argument I made a minute ago about the rarity of a chain end. And of course, as the branches get longer, the chain ends get rarer. But as the branches get shorter, the chain ends get more frequent. All right, so you can kind of engineer this based on how far that branching goes. We do know that regardless of anything that's shown here, the presence of branching boosts the viscosity a lot. Hopefully that makes sense to you now, just because for these chains to move around, bless you, in solution requires this coordinated motion, and those areas of branching are going to resist that. Oh, yeah, so viscosity. This table has a high viscosity, all right, and air has a low viscosity. Sometimes people need that benchmark. You're not used to seeing viscosity, so make sure that you understand that that's the way viscosity goes. So in this context, though, these branches can hinder rotation and translation, can act like large side groups, which can in turn increase TG. So if we look at just regular old linear polyethylene, minus 90 is the glass transition for polyethylene. This particular version of branched polyethylene has a TG of 110. All right, and so what that means is the presence of all these chain ends is having an effect. All right, and dropping that glass transition down to minus 110. So it takes less energy to get this through the glass transition than it does regular polyethylene. Does everyone see that? All right. And then something we've talked about a little bit is the fact that when we have cross-linking present, it reduces the chain mobility, and so the glass transition should increase. So normally we think about linear systems, but when we have a low cross-linking density, what we can do is we start to, in the area of where these guys bond together, we start to restrict the motion of these, everything that's in the immediate area of that crosslink. So it's like the inverse of a chain end in terms of its effect on free volume, and especially in terms of its effect on mobility. Those are restrictions, and again, it's carbon-carbon bonding, all right, and so it's going to have a very strong effect on mobility in that local area. Now, of course, we talked about this a little bit as well, as this distance increases, all right, the area between those regions of cross-linking becomes longer and longer, and you have more chain that acts like it's in a linear system. All right, so if cross-linking is rare, then you may have areas of the polymer that exhibit normal glass transition temperatures because there's so much of it that's unrestricted by these cross-links. Hopefully that makes sense. And then if we go the other way, of course, then we make these cross-links more frequent, all right, and we're going to drive that glass transition up as a result of that behavior. So the inherent glass transition temperature of the unrestricted chain is a starting point, and you start making it more and more difficult by adding more crosslinks. Does that make sense? All right, plasticizers. We all know what those are, as we should. These are low molar mass additives. They act to spread the chains apart. They also act as a lubricant, and they can mediate the chain-chain polar interactions, usually decreasing them and adding free volume in the process. All right, so these are polymeric in nature, but they're not really high molecular weight polymers at all. All right. They have an affinity for whatever it is they find themselves in. Otherwise, they wouldn't stay there. They would spontaneously go to the surface because they're not long chains. And they increase the free volume in the system and help make things more ductile. That's the whole point of plasticizers, is to achieve that goal. And so the one we always talked about, ethyl hexyl phthalate, diethyl phthalate to neat PVC, can significantly lower the glass transition of that particular material. So normally it's 87 for the diethyl phthalate. Ethyl hexyl phthalate is minus 80, and this is I think I don't know if you've seen these structures before, but this is the picture of this particular phthalate. And note that we've got a couple of different things going on here. We've got that polarity there, and so we need that polarity to go and mingle with PVC. All right, so this is actually very important, this engineered structure. And then outside of that, we have all this non-polar structure, all right? And so that helps make space, all right, and allows for this basically to swim around inside the PVC chains and keep them apart. But this allows it to go in and stay there, and then this provides that space between the chains that acts like, a little area of polyethylene, basically. Compared to all the chlorine that's in there, this is eliminating a lot of that secondary bonding between the chlorine-containing chains. Does that make sense? All right. And what the diethyl phthalate can do is decrease the glass transition to a condition that's lower than room temperature, but maybe not very much lower. We talked about this. You engineer the glass transition to be somewhere in the neighborhood of room temperature. All right. And so normally that's what we do with plastics. Of course, if you're working with PVC, that might go outside. So maybe you want to engineer the glass transition so that it's within the range of normal outside temperatures, like minus 2 degrees centigrade, something like that, just so that it's not too brittle at low temperatures. But typically, we want things to be flexible at room temperature, and a PVC-based seal is a very good example of that. You want something that has the ability to cause sealing, and so therefore it must have some softness associated with it. Any questions about that? Okay, now we get into this kind of a synthesis of things we've been talking about here, the TG of copolymers. So we have learned that copolymers have a lot of different structures, and you can get many different behaviors based on a blend between polymer A and polymer B. Polymer A and polymer B can be AB along the chain. They can have a huge block of A and a huge block of B, and those will have different properties. All right, and so this is an example of that. If we have random copolymers, they tend to be homogeneous single-phase polymers, and the glass transition is usually some type of intermediate between these two different homopolymer stages. And so if we want to calculate the glass transition of a single copolymer, then we can look at the weight fraction of A times the glass transition of that polymer A, and the weight fraction of B times that glass transition of polymer B. All right, and so it's just basically a molar division of what's in there, and you have a true rule of mixtures behavior as a result of that. So you keep that in mind. But if we go the rest of the way, though, and go back to the concept of block copolymers, where again you have a long section of A and then a long section of B, all right? So two different scenarios here. You can, in the DSC, pick out, let's just call this one, call that the other. When it's done in that way, and you have distinct areas of one and distinct areas of the other, it should make sense to you that you'll be able to see those individual glass transitions, because they become large enough that they can do what they would normally do if it was phase pure A and phase pure B. All right, so that should make sense. I do want to point out that this is actually backwards. That glass transition in DSC, if you ever get into this area, glass transitions can be a lot more difficult to see than melting points. All right, so many times we looked at PCL, of course, and there's a little dip there at minus 90, and then the melting point is this huge trough. But TG is sometimes very difficult to see, so this is definitely an ideal case when you pick out both of those. But it is possible. Whereas if you don't have a block copolymer, not a block copolymer, this is where we look at this rule of mixtures behavior, where you have A and B, and they're so admixed together that you don't have regions. And so you just get this average TG for that system. And that's not necessarily a bad thing. Maybe this gets you right where you want to be, just below room temperature. All right? And you can pick the amount of A and B and move this around based on what your needs are. Again, part of the beautiful tailorability of plastics. Oh, yeah, I did want to bring this up. So we have loss modulus and storage modulus, which can also reflect the individual regions. And so we can affect that. You guys learned about this, right? In one of the lab classes, right? Yes, some of you remember that? All right, so this is a different way of looking at thermal transitions, but has to do with the amount of energy that a system sees when it's being stimulated mechanically. But those will also depend on what type of polymer systems are in play. TG of polymer blends. The glass transition temperature of a miscible one-phase blend is usually intermediate between those of the two components. So again, we're looking at this rule of mixtures type behavior, and we can, when it's that well mixed, plot this. One example of a polystyrene polyphenylene oxide amorphous blend, and you just change the amount of the PPO, the polyphenylene oxide, and as that amount goes up, it goes from the glass transition for polystyrene to the glass transition for polyphenylene oxide. All right, so not a big deal. This is what you're used to seeing. All right, and so a lot of materials people are trying to get outside of this, one way or the other, not follow little mixtures. But this is what you'd expect for those types of amorphous blends. Okay, that seems pretty obvious, hopefully. And then we need to think about crystallinity. So this gets into a more advanced concept. And so at the very beginning, I told you guys, and you should know this already, that we think of TG for the amorphous and TM for the crystalline. But as we've talked about a number of times, when it comes to X-ray diffraction and some other areas, there is an interfacial effect with polymer systems. And especially when you go to an extreme of crystallinity, then you can start to see some of this. Not so easily spotted sometimes because TG, as I said, can be kind of weak, and you add in crystallinity, meaning that the amount of amorphous content is much lower, then it becomes hard to see. But it should make sense to you that semicrystalline polymers display glass transition, but only for the amorphous component. For high crystallinity polymers, the glass transition is often hidden or masked since the amount of the amorphous component is very small. All right. However, if you can see it, TG is often increased due to the crystallized restricting chain motion. And this should make sense. And it's not entirely a theoretical concept. This has been observed. It's not easy. So we have what we've been talking about, the boundaries between crystalline and amorphous. All right. We treat this as the two-phase model, as you recall, where everything is defined and it's either in or it's out. All right. But it should make sense to you, knowing what you now know about glass transition, that there is going to be an area near those crystals where the amorphous component is affected by the fact that it is connected to the crystalline component. And you kind of sort of see this in the cartoon, that the density of chain starts to go up where it has to go in and out of the crystalline phase. And so there is an in-between region there where the polymer chains are restricted, and so it makes sense that their glass transition is going to be higher than what it would normally be. Does that make sense? Normally we don't like to think about this. We like things in black and white, but the reality of it is that you can sometimes see this in very highly crystalline polymers. Any questions about that?
So basically the crystalline parts don't change enough for TG to have a noticeable effect?
The crystalline parts don't have a TG. The region near the crystal is going to have its mobility decreased, so therefore its TG is going to go up. But it's just it's a halo effect, basically a halo around the crystals. Does that make sense? Bless you. Okay, and closely related to that is the effect of pressure on glass transition. TG increases with increasing pressure. Why is that? Just evaluate the statement, don't look at the graph. Why is the pressure going to go up? Why is an increased pressure going to cause an increase in glass transition? Yes?
I mean, it makes me think of like PV equals nRT.
Uh-huh.
But I don't know if that is on the right track.
It's in the right direction. This is one of the A and B terms. Yes?
It's free volume.
Free volume, yeah. So you're going to squish this polymer by applying external pressure. And when I mean squish, it's just you're applying external pressure, and that pressure is translated throughout the entire volume of the plastic, all right? And so it affects the A and B terms and the PV equals nRT, and decreases the amount of space between the polymer chains, all right? And so that's what's shown in this data, in which we're looking at glass transition for polyvinyl acetate, and this is a kind of a screwy curve, but this is pressure at 10 to the 7th pascals, and as we increase the pressure from 0 up to 8, 10 to the 7th pascals, you see the glass transition go from whatever that is, a little bit more than 30 to a little bit more than 50, I think, for this given polymer system. All right, so relatively large changes in pressure, they bear down on the free volume, squeeze it in a little bit, and it takes more energy to cause this thing to transform from one glassy state of matter to the higher volume glassy state of matter. Does that make sense? All driven by free volume, this really weird concept that exists in plastics and has a lot to do with mechanical properties, diffusion, a variety of different aspects of plastics. Any questions about that? That should make some sense. Not the first time we've seen pressure make a difference in polymer properties. All right, so the next thing is hopefully something you've seen before. It has to do with artifacts, really. The effect of thermal heating rate on glass transition. And so if you are heating a polymer at 1 degree per minute, first off, these polymer samples tend to be pretty small. They, like 100 milligrams is considered a large specimen. But even in those small amounts of polymers, we know that polymers are crappy thermal conductors. So if you heat at 1 degree C a minute, maybe it doesn't make a big difference. But if I heat at 10 degrees or 50 degrees a minute, which is kind of crazy, the furnace may say, oh, I'm at 100 degrees, and the polymer may say, hey, I'm only here at 40. I haven't gotten to anywhere near 100 because it's such a lousy thermal conductor. And so that can cause these observed artifacts in the systems that might make you think that the glass transition is something other than what you read in the book, for example. So what you might see is the observed glass transition becomes lower as the experiment is carried out at slower heating rates. Let's leave it at that. And what that means is that you're getting the right glass transition if you go slower. And so if we heat at 0.02 per hour, all right, so very, very quick, or we heat over a certain period of time that requires 100 hours, all right, we're going to get a more realistic view of the glass transition if it takes 100 hours to heat that specimen. Not that anyone does that. I mean, typically, what you see in the literature is 0.5 or 1 degrees, and that's a slow heating rate. 10 degrees is considered a fast heating rate. But that 0.1 is going to give you a more realistic value of glass transition. So you might see an actual glass transition to 24 degrees, but if you heat at over 0.02 hours, it may tell you that it's 33 degrees, which is crap. All right, so this data is showing you that for a given heating rate or a given heating time, you get 2 different glass transitions. It's not that the polymer is behaving differently, it's just the amount of time it takes for heat to be transmitted into that polymer is being accounted for if you heat very slowly. Okay, does that make sense? And what it says when you publish TG data, now it's my turn. Thank you. It doesn't blow anybody's ears out on the recording. When we publish TG data, we need to provide details regarding the conditions of the experiment and what was the heating rate that was used. Otherwise, people might not believe us. Okay, and so moving on to the crystalline state, polymers are not normally crystalline due to the long chain nature and chain entanglements. All crystalline polymers are semicrystalline, exhibiting both amorphous and crystalline regions. You've seen this cartoon before. Crystallizability depends on the regularity of the chain structure, isotactic, syntactic, atactic, etc., molecular weight, intermolecular interactions. All these things are familiar to us. When we think about polymer crystallites, we've already gone over the fact that when crystallized from dilute solution, you remember that, we get these very pretty pictures, all right, that in this case that's a 5 micron bar, so it's maybe 10 microns across, but it's only a couple hundred angstroms thick, even under those highly idealized conditions. So it's not like we can do something useful with this other than figure out what the shape of the crystal should be. When we crystallize from more concentrated solutions, you can get these multi-layered dendritic structures that can be formed, as is shown here. So think of remember the sticks of chewing gum. Remember the intermediate concentration where they multinucleated out of one point? That's kind of what you're going to see under most real circumstances, as is shown here. For a thin film of some polymer crystallized on the surface, you get these spherically shaped crystalline structures in 3D, but on the surface it's just a film in which the crystallites have intersected with each other and stopped growing. So nothing. In spherulites, crystalline lamella are usually spherically and symmetrically distributed. And so this is a little bit more advanced than what we talked about before. So we have that central nucleation and growth point, and it goes out and it stops out here at the boundary, and the rest of that remains amorphous. And we know things started from this point. But if we zoom in on some of these things, we can see that it is kind of chaotic. You know, we know that over there is where it all got started, and things are kind of radiating out from there. But there's all these cockeyed angles. All right, so they don't communicate well with each other. They don't all go out perfectly parallel radially from that center. They run into each other and they stop each other's growth, and then something else picks up from that. All right, so these things are very chaotic, and as you can see, you know, every one of these tiny lines is a crystal. So, you know, even for this relatively small spherulite, you've got thousands, if not millions, of individual crystals in these systems. And of course, there's also amorphous content present in the systems as well. And so these have distinct melting points, much like what we saw with the glass transitions. Cis polyisoprene, you know, it's got this specific structure that you guys are now familiar with. That's CH3, and there's a hydrogen here. And so we can take that and compare it to polypropylene, which is the non-double bond containing analog. And so in that context, polypropylene has a melting point of, for this particular one, 171. You guys might remember different ones on the test. But when we make the polyisoprene version of that, it drops to 28. Why is that? So these are both polymer chains, all right, and they go off into infinity. What's the difference between polypropylene and this? Yeah.
Double bond?
Double bond is one difference. What else is different? I mean, double bond should make it go up, right? Not down. So what's the other key difference? Yeah.
Would it be because it's a cis polymer?
Well, I mean, compared to trans, yeah, there is a difference there. But the main point I'm trying to make is that you've got 4 bonds per carbon, right? And so what that means is there's an empty space over here, all right? And there's an empty space over there. In the case of polypropylene, those spaces aren't empty. We have 1, 2, 3, 4 bonds for this carbon, 1, 2, 3, 4 bonds for that carbon, and that involves 1 hydrogen here. There's nothing over there and nothing over there. And so that's one of the reasons why the cis polyisoprene has such a low melting point, is because it's easy to move those chains when they don't have neighbors to bang into. Okay? Does that make sense? CH3 is the same between both plastics, but that free space means that the chains can move around more easily, even though we've got this rigid double bond in the system. All right. So it has to do with how much energy does it take to extract that polymer chain from a crystalline structure. Okay, and so DSC, looking at TM and crystallinity. You guys have seen this before, and again, you know, this is showing you, in my mind, this is an exaggeration of what glass transition, and this is typically much easier to see. Area under the peak is the heat of fusion, and what we're going to do today is show you how to calculate crystallinity from fusion for the system. And this is for isostatic polypropylene. The melting point is 165. All right, so the delta HF for crystalline component is shown in the peak is 97.2 joules per gram from that particular experiment. There is a theoretical delta HF, which means that if you could make polypropylene fully crystalline, which you can't, but if you could, it would have a melting energy of 8,790 joules per mole. And so we need to first take this data in joules per gram and turn it into, or take the original data of the theoretical peak and turn it into joules per gram. So we find that 8790 divided by 42, which is the molecular weight of polypropylene, is 209 joules per gram. And so that means that this particular material has a crystallinity of 46% based on the ratio of those two. All right. So I can give you this problem on a homework or on a test, for example, and you can crank out the percent crystallinity. Right? We do this many times in the lab. This is not hard to do. Any questions about that? Factors that affect the melting point of these polymer crystals. Again, regularity, flexibility, close packing ability, maybe more here than glass transition, and intermolecular interactions. All these things, again, relate to how easily we can extract those chains from the polymer crystal. And if we look at this particular structure, which is basically PET, but we have the ability to vary what R is. Polyethylene terephthalate, melting point of 265. Polypropylene terephthalate, melting point of 220. Why is that different? Because that length of polyethylene-like chain is now longer. All right, so we have more flexibility. It takes less energy to extract these chains out of the crystallized structure than when there's only 2 carbons in that group, and it's a pretty large effect as well. All right, polybutylene terephthalate is far more important than polypropylene terephthalate, but that's not being discussed here. And if we look at flexibility, we can also look at these R groups as well. And so we plug in R prime here in this particular structure, so we're basically kind of messing around with the initial PET structure where we have a melting point of 265. We put in 2 of those, it goes to 355. That should make sense. All right, it takes more energy to get these big, bulky phenyl groups out. There's 2 of them. All right, it's going to take more energy. We instead get rid of the phenyl groups entirely, and it drops to only 50. All right, so the ability to extract polymer chains depends on how much energy it takes to make them vibrate, make them move, make them come out of that crystal structure. Any questions about that? Should be for that one at least. And then of course we also have intermolecular interaction in these systems. And so again, we're doing the algebra thing where we have this PET-based structure. And the R double prime in this context, if it's a little bit of polyethylene, the melting point is 170. Polyethylene has no polar bonding capability, right? So that means the bonding between itself and many of its neighbors can be relatively weak, although we do have, of course, things in the structure that are capable of polar bonding. But if we swap out some of the polyamide type structure, now we're adding back in nitrogen, which is capable of hydrogen bonding with its neighbors, all right? And our melting point jumps back up to 273 as a result of that. All right, so we can engineer those melting points, also knowing that it's engineering the mechanical properties at room temperature. Okay, suppose you could synthesize polymers A and B. Would you expect syntactic A and B to have the same melting point? No, absolutely not. All right, you've got chlorine here.
Very highly reactive side group.
What's that?
Very reactive side group versus very unreactive side group.
Reactive? Oh, you mean if you were trying to make them?
Yeah.
Yeah, but if you had made them, all right, you'd expect some very different glass transitions based on the fact that one is capable of polar bonding and the other one is not. All right, if we increase the size of the side groups in the linear polymer, it will decrease the melting point due to less perfect polymer chain packing. And so again, the algebra thing, polyethylene, and then we have CH2, CH3, 3, and then 4. All right, you make these longer. We start making it easier because the chain ends are further away and they can flap in the thermal breeze. You guys remember that analogy? All right, and that drives our melting point down. It's easier to extract them because they're further away from the main chain and they have more mobility. These are all chain ends. It's just the chain ends are getting further and further away from the anchoring point of the main chain itself. Okay? That should make sense. And like what we saw for glass transition, cross-linking continues to decrease the general mobility of polymer chains and thus can increase the effective melting point. All right? And that should make some sense that if it is in a crystal structure, then it's going to make it more difficult to move out of the crystal structure. However, highly cross-linked polymers do not have a melting point because crystallinity cannot form in these structures, or if it does, it will be very small. And so what you see sometimes, especially in the rubber literature, they do something where you have a rubber, which, as you know, is a kind of a lightly cross-linked polymer, right? Otherwise, it wouldn't snap back. And if the length between those cross-links is large, you can get crystallinity to form. All right, and then the neat thing is you pull on that rubber and the crystals disappear. All right, it becomes amorphous, and you let go of the rubber, it goes back to being crystalline again. All right, that kind of speaks to how fungible crystallinity is in these polymers, that they can go back and forth just based on mechanics alone. And that all has to do with how rare these cross-links are in these structures. You know, how much space exists between these bonding points. And if there's not much space, everything is cross-linked, no crystallization occurs whatsoever. All right. Still a really brittle, rigid structure, even in the absence of crystallinity, because everything is cross-linked. All right. So you can definitely engineer these properties one way or the other. But in some cases, you can have crystallinity form depending basically on how much space exists between those cross-link points in these structures. Any questions about that? All right, and then last thing for today is the effect of molecular weight on TM. And as we've discussed before, high molecular weight chains may not be as easy to crystallize as a low molecular weight chain. So we talked about the hydrolysis of PET, all right, and as we snip it away at the PET chains, not at the ends, all right, anywhere within the polymer chain, it's going to react with water. So it could react at the end, it could react right in the middle. It's not restricted to just the ends. And when those chains get shorter, TM starts to go up, all right, because you can make more perfect crystals. Same thing is true for molecular weight. When molecular weight is really high, it's kind of hard to move these big old sluggish chains around, all right, and so the crystals that form tend to be not very perfect. Okay, so you can actually have a lower melting point for high molecular weight polymer chain. All right, and all it has to do with this effect of chain mobility and the fact that it can prevent what's called the orderly packing in these systems. All right, and this is a couple of cartoons that don't really tell you what I just said, unfortunately. This is not actually all that representative. Any questions about all that? All right, when is the test? Wednesday. All right. And hopefully I'll be posting the exam answers sometime tomorrow, I suspect. Okay, anything else? All right, see you guys on Wednesday.